Hello, and welcome back to the course. So today we're going to talk about simply connected domains again. This is part 2 of section 4.3 in the book. So what we're going to do today is we're going to look at list of equivalent conditions for a domain in C to be simply connected. So first, of course, we'll say, first on the list is U is simply connected. So it's going to be, all of these things are going to be equivalent to this thing, right? U is simply connected. And we're talking about the homology sense, which is that for if we take any cycle in U, then the winding number around any point in the complement is 0 with respect to the cycle, right? So that's our definition of simply connected. As we said last time, this is not really the right definition. It's equivalent to the correct definition, which is really in the sense of homotopy. But we're not doing homotopy. We're only doing homology. So we want to talk about simply connected. And so we made the wrong definition. But it should be. That is fine in C if we're talking about just domains in C, right? So open connected subsets of C, right? All right. So the first thing that's first condition that is equivalent to being simply connected is that every holomorphic F in U has a primitive. So every holomorphic F is a derivative of a function, of a holomorphic function. Or a holomorphic function in U, right? Now that's equivalent to every non-zero F, right? So now every F that has no zeros. So it's not zero anywhere in U, right? So for every non-zero F, right, or nowhere zero F, sorry. So every nowhere zero F has a logarithm, right? So for every nowhere zero holomorphic F, we have a holomorphic G, such that e to the G is F. Now that's equivalent to, well, here we said every holomorphic F has a primitive. So how about just looking at 1 over Z minus P for every P in the complement? How about if that has a primitive? And that's equivalent to, well, for every holomorphic F and every cycle in gamma, we have that the integral of F over gamma is 0. And that's equivalent to the to the following, that for every P in the complement of U and every cycle gamma, the integral around gamma of 1 over Z minus P is 0. All right. So let's prove this. So we proved last lecture that 1 being simply connected is implies that we have primitives. We also proved that if we have primitives, we have logs, right? So we have 3. So we've proved that already. So 1 implies 2 implies 3. We've proved that. So let's suppose 3. Let's suppose that we have logs, right? Take a point in the complement and find a G such that e to the G is equal to Z minus P. Now Z minus P is a nowhere zero function, a holomorphic function in U, right? Because P is in the complement. So yeah, I can find a G by if 3 is true, right? Now let's look at the function 1. 1 is the derivative of Z minus P, right? Now, Z minus P itself is e to the G, right? If I differentiate e to the g by chain rule, I get e to the g times g prime. Now, e to the g, let's use this equality again. E to the g is z minus p, right? That's how we really define g, right? That's what g was. All right. Well, that's exactly for that we have that 1 over z minus p as a primitive, right? So we had the existence of logs implies existence of primitive of 1 over z minus p for every p in the complement of u. Now, by Cauchy's theorem for derivatives, right, which said that if that's the first version of Cauchy's theorem that we proved, was that every time we had a function which was a derivative, right, which was a derivative of a holomorphic derivative of something, that over every cycle we just got 0, right? So yeah, so if 1 over z minus p is has a primitive, therefore it's a derivative of something, well then the integral over any cycle is 0, right? So we have 6. That's what 6 was, right? For any cycle and any cycle in U and any p in the complement, we had that the integral of 1 over z minus p over gamma was 0. Now, what is the integral of 1 over z minus p? Well, if we divide by 2 pi I, you get precisely the winding number, right? That's by definition the winding number. So, what is 6? 6 is precisely basically just a restatement of our definition of simply connected for every cycle gamma and every p in the complement. The winding number, which is this integral, right, is 0, right? So every cycle gamma, every p in the complement, sorry, the winding number is 0. Therefore, that's the same thing, right? So we have an if and only if. We've just written 1 in a funky way. So 6 is nothing more than 1, right? Now, we haven't touched 5 yet, right? So we've gone all around, but we skipped 5. So by Cauchy's theorem for derivatives, we have that 2 existence of primitives implies 5, which was that the integral over any cycle of integral of f over any cycle gamma was always 0 for any f in any cycle, right? So we basically have Cauchy's theorem in U, right? For any gamma, right? And for any f. That was 5, right? Well, if we have 5, we have 6, which was just, not for every f, just for those guys. But yeah, those are holomorphic functions on U, right? So 6 is just a special case of 5. So 5 implies 6 as immediate. There's nothing to prove. All right, so what we proved was basically, I guess the hard bits we've proved last time, right? So this was just, putting it all together, right? We started with 1. Then from 1, we went to 2. Well, we did it last time. And from 2 to 3, again, we did it last time. Now from 3, we went to 4, right? we had that if we have logs, then 1 over z minus p has a primitive for every p in the complement. Once we had that, we applied Cauchy's theorem for derivatives because z minus p had a primitive. So yeah, the integral around any cycle is 0. So we got 6. And then we said, well, 6 and 1 are just one and the same thing. Right, so that was the first, run around, and we're still missing 5, but 5 was implied by 2, right? And 5 immediately implies 6. 6 was just a special case of 5, right? So, okay, so that proves that we got all of these as equivalent conditions, because you can go from any condition to any other one by a sequence of implications. All right, now there's a couple of other things that we can put on this list, that one would normally put on this list. First is the existence of roots. Now that's a little bit harder to do one direction, so it'll be easier to prove later. Another one that is also just one direction, that will also be easier to prove later in both if and only if. So there's also going to be an if and only if. And it's one that is somewhat different, right? So the roots, that seemed very similar to, that was sort of like the logs, right? Once you had logs, you had roots, right? But I guess the tricky bit is, well, once you get roots, you get logs. So, but this one is going to be, this is slightly different from the other ones. So this is a more topological one. It's an easy one to check, right? So if you have if you have a domain, this one is relatively easy to check, right? I mean, all of these things about like all winding numbers and right, and when does something have a primitive and so on, those are hard to check. This one is easy to check, right? So suppose that we have a domain in C. Now, if it's a domain in C, it's a domain in the Riemann sphere as well, right? So we can look at the complement of U in the Riemann sphere, and that's important that this is the Riemann sphere, not C. It's not C minus U. It's C infinity minus U. It's the Riemann sphere minus U. If the complement in the Riemann sphere is connected, then U is simply connected. Okay, let's prove this. So let S, just so that I have to write this whole thing, right? So let S denote the complement in the Riemann sphere, right? So it's a complement of U in the Riemann sphere, and let gamma be a cycle, any cycle in U. Now, take phi to be a function, well, the function, the following function, defined on all z in the complement. So it's defined on C minus gamma, so complement of gamma, right? Which is the winding number of gamma around z. So you can define it for any z that's not on gamma, right? Now, we know that this is a continuous function. It's actually constant on components, right? But yeah, it's a continuous function on C minus gamma, right? Therefore, it's continuous on S minus infinity, which is, well, that's a subset, right? So it's a nice continuous function there, right? Now, on the unbounded component of C minus gamma, another thing that we proved before, right? It's not just continuous, not just constant on the components. It's actually 0 on the unbounded component, right? So phi is 0 on the unbounded component. So it's a 0 on a neighborhood of infinity in the Riemann sphere, right? Now, I mean, phi at this point is not defined at infinity, right? So except for and except for infinity, right? So wherever it is defined on a neighborhood of infinity. But that means that we could just set it to be 0 at infinity, and we have a nice continuous function not on c minus gamma, but on c infinity minus gamma, right? We've added one point, right? And it's still continuous there, and it's 0 at infinity, right? And therefore it's continuous on S, right? Now S is contained in a single component of c infinity minus gamma, right? I mean, phi is constant on these components. And why is S contained in a single component? It's because S is connected, right? Here, this is where we use that S is connected, that C infinity minus U is connected. Up to here, I mean, this is just not that held for everything, for every U. But now, this is where we use it, right? So we have, so S is contained in a single component of C infinity minus gamma, or another way you could argue as well. I mean, phi is continuous on S, and S is connected. So phi is restricted to S is constant, right? I mean, it's a locally constant function that's continuous on a connected set. Therefore, it's going to be constant on that set. All right, now, phi at infinity is 0, infinity is in S, therefore, phi on S is identical 0. And that's, from that we get that U is connected, because gamma was an arbitrary cycle in U. So, for an arbitrary cycle, an arbitrary point outside U, right? So arbitrary point in S, right? We have that the winding number of gamma around any point in S is 0. Well, that's true for all gamma and all Z in S. We get simply connected. So again, this is an if and only if. This is not just just one direction, but it'll be easier to prove later on to the other direction, right? So if U is simply connected, then C infinity minus U is connected. So that's actually interestingly harder. So it's maybe one remark about why is it harder. It's harder because we have to construct gammas. That's the bit. All right. So why is it important to use the Riemann sphere and not C? Well, you could just take C minus 0. So C minus 0 is, well, that's not simply connected. The puncture plane is not simply connected, right? Log of Z is a function that well, it's the non-existent primitive of 1 over Z, right? So 1 over Z does not have a primitive. This is not a simply connected domain. But the complement in C is just 0. That's a connected set. So C minus U in this case would be connected, but the domain is not simply connected. But that's because we're not supposed to look at C minus U. We're supposed to look at C infinity minus U. And C infinity minus U here is 0 and infinity, and that's not connected. So, right. So it's important that you use the Riemann sphere here. All right. Just a quick exercise. It comes up actually quite often that you want to because a lot of times you can let's say get primitives right? So maybe you want a primitive not just on some small set, you want a primitive on some larger set, right? Well, can you put, a simply connected domain together out of smaller simply connected domains? And it's not quite true. You cannot do that. The union of two simply connected sets is not necessarily simply connected. So the first bit in this exercise is to find such an example. So find two simply connected domains such that their union is not simply connected, right? And I claim you've seen this already in this course. Basically, make it C minus 0, right? Make that the union, right? That's a union of two simply connected domains, right? And you should try, make sure that it's a domain, right? There's going to be a domain that's not simply connected, right? So that's one thing that could happen, right? I mean, you could have like a union of two disjoint disks, right? It's not even a domain, right? It doesn't make sense to talk about it, but it's. But suppose that the intersection is non-empty, right? Now, if the intersection is non-empty, then if it is disconnected, you might not have you might end up with something like C minus the origin, right? But if it is connected, so if you have that the intersection is non-empty so that you get a domain and it is connected and your two domains are simply connected, then their union is simply connected. But you need the fact that their intersection is connected. Otherwise, it's not true. All right. So that's it for this this lecture. So next time, what we're going to do is so simply connected domains are domains without holes. Right. So next time we're actually purposefully going to start thinking about, well, what if we have holes? And can we define actually a version of power series on things with holes? So like, for example, on the punctured plane, if I'm missing the origin and I have a holomorphic function, then, outside the origin, can I do something like a power series? Well, not a power series, like 1 over z, for example. It doesn't have a power series. But what we can do is we can define a series of powers, the Laurent series, which is, well, we just have to throw in all the negative powers, like 1 over z, for example, right? And then we can write this power series, not quite power series, this is the Laurent series, right? So that's what we're going to look at next time, is the Laurent series development. All right, so see you next time.